Hello Internet, welcome to another tutorial on Smith chart. This is the second tutorial in the series. In this tutorial we'll draw the Vswr circle on Smith chart to find voltage standing wave ratio. It is super easy to find standing wave ratios on Smith chart graphically. We need to plot normalized impedance and then we'll draw a circle and find VSWR. As simple as that. So let's begin. I'll take up an interesting case. I'll take up a case where I have three different types of load. ZL1 is 50 plus 100 iota. ZL2 is 50 minus 150 iota. ZL3 is 50 ohms. So what we'll do is we'll plot VSWR circles for all these three and we'll find VSWR for these three loads. Before we go to the Smith chart, let me just tell you briefly about what standing wave ratios are. Whenever you have some generator sending signal on a transmission line to the load, you've got signal going this way and reflections coming this way. This is undesirable thing, and what will happen is this wave which is colliding with the incoming wave will add up at some point or will subtract at some point, causing this kind of a structure. This is the reflected wave is adding up to the incoming wave at some points, giving it V max and subtracting it at other V min, and the ratio of V max to V min is VSWR or SWR to be precise. Please understand SWR occurs because of reflection, so there has to have a formula which should consider a reflection coefficient into account, and reflection coefficient itself is nothing but this is the load impedance and this is the characteristic impedance of the transmission line. So pretty simple concepts, and we want this thing to be not high. This is what we want, and we want this thing to be 1. And when will this thing, we want reflection coefficient to be 0. In fact, we don't want this to be 1, we want it to be 0, and when this will become 0 is the case of no reflection, and that will happen when ZL becomes equivalent to Z0. And in this case I'm assuming the Z0 to be 50 ohms, so you can expect no reflection to occur in the third case. So this is what the brief idea about standing wave ratio and reflection coefficient is. Now let's get to the Smith chart. This is the Smith chart, and I talked about Smith chart in my previous video where I tell you that this part, this line is the resistance line, these are the reactance circles, half circles are reactance circles, full circles are resistance circle, the lower half circle is capacitive reactance, upper half circle is inductive reactance. So anything positive will be plotted on the upper side, and anything negative will be plotted on the lower portion of the Smith's chart. But we'll need to find the normalized impedance first. Normalized impedance will be this divided by 50. So 1 plus 2 iota, 1 minus 3 iota, and 1 of course. And let's go ahead and plot this thing. So in order to do that, this is 1 plus 2 iota, so I'll take up the 1 circle and I'll take up the 2 circle on the positive side because this is 1 plus 2 iota. I'll mark this point here. So this is my normalized impedance point for load 1, ZL1 dash. And I'll go to the 1 circle and I'll go to minus 3. Minus 3 is here. So this is the point of ZL2 dash. And this is my third point, ZL3 dash. So let's find VSWR. VSWR. Now to plot VSWR, what we need to do is we need to take compass. We need to place the compass needle at the center like this, and the radius is calculated from the point on the normalized impedance point, and draw the full circle. Full circle is drawn, but technically we don't actually need a full circle because we simply want that point which the circle cuts on the right hand side of this straight line. But nevertheless, we'll do it anyway. And I'll go back and extend this radius for the second normalized impedance point. And I'll draw a bigger circle. Now we're getting an idea of the point that it cuts. On the now this point is this is 4, this is 5, and this is 10, 6, 7, 8, 9, 10. So this point is 6. So this is the VSWR, as simple as that. So VSWR for ZL1 is 6. How cool is that? And let's see, this is 10, and this is 20, so this must be 2 or 1, 2, 3, 4, 5 divisions between 10 and 20, so each division must be 2, so this is 12. VSWR is 12. And this is a dot circle, so VSWR is 1. So I've got a VSWR of 6 here, 12 here, and 1 here. Now if you were to, and this is how simple it is, you take the compass, take the radius, and draw a circle. The circle cuts this line on the right hand side, and the value on the right hand side is show VSWR. And this is so super easy to calculate. On the contrary, if we were to find VSWR mathematically, we would have to find the reflection coefficient first. So let's find the reflection coefficient of ZL1, which will be a lengthy process because ZL1 is 50. Reflection coefficient for the first load, that will be ZL1 minus Z0 on ZL1 plus Z0. So 50 plus 100 iota minus 50 iota, 50 plus 100 iota plus 50. So this is going to be 100 iota upon 100 100 plus 100 iota. Then you will need to take help of the calculator to find the magnitude of rho, and that magnitude would be substituted here to find VSWR. That would have come out to be 6, and similarly in the second case 12 and 1. So if you wish to skip all those lengthy mathematical calculations, this is the solution. And thank you so much for watching this video. I hope this video helped. I'll come up in the third installment of this series where we're going to learn how to plot the reflection coefficient. Thank you so much for watching. Have a good day ahead. Bye.